Hello students, welcome to our third video of chapter 13 Amines. In this video we shall study about the basicity of amines. Basicity of amines. The basic nature of amines is due to the presence of a lone pair of electrons on the nitrogen atom. As seen in this structure, nitrogen atom is a sp3 hybridized atom. In case of primary amines, it is attached to one alkyl group and two hydrogen atoms with strong bonds. The lone pair of electrons left on nitrogen atom remain in the fourth sp3 hybridized lobe. Amines are Lewis bases as they share a lone pair of electrons on nitrogen atom with an electron deficient species. For example, trimethylamine on reacting with BF3 forms an adduct trimethylamine and BF3, which has a positive and negative charge. In this adduct, the nitrogen atom has donated pair of electrons to boron trifluoride, which has incomplete octet. Boron trifluoride is having boron attached to 3 fluorine atoms, thus having only 6 electrons in its last shell. It accepts a pair of electrons from nitrogen atom, thereby completing its octet. This formation is called an adduct, and the type of bond formed between these two is called as a coordinate bond. Basic strength of amines is expressed quantitatively as Kb or pKb value. In terms of Lowry-Bronsted theory, amines are basic in nature and are explained in following equilibrium. Any amine when reacting with water forms a conjugate acid by accepting H+ ion from water molecule. In this equilibrium, amine has accepted H+ ion and formed a conjugate acid along with OH-. Hence, an amine is a Lowry-Bronsted base. For stronger base, this equilibrium shift towards right-hand side, that is, conjugate acid should be stronger than the amine itself. Thereby, the Kb value is large and the pKb value is smaller. The following table gives us the pKb values of some amines in their aqueous medium. Let us see them one by one. In primary alkane amines, we observe that ethanamine at second position has the lowest pKb value of 3.29. So it is the strongest amongst the four. For secondary alkane amines, N-ethyl ethanamine has a pKb value of 3, which is lesser than the previous one. Hence it is stronger. In case of tertiary alkyne amines, N-diethyl ethanamine has a pKb value of 3.25, which is less than the pKb value of N-dimethyl methanamine. Hence it is stronger. Ammonia is a weaker base as compared to the aliphatic amines, having a pKb value of 4.75. As you go below to the arylamines, we observe that they all are very weak bases having a very high pKb value ranging from 8.92 to 9.38. Let us see the basic strength of aliphatic amines. The trend in the observed pKb value and basic strength of primary, secondary, tertiary amines and the ammonia molecule can be represented as follows. The order of pKb values is: ammonia has a greater pKb value than RNH2 and it is having a greater pKb value than the secondary amine. However, the secondary amine has a lesser pKb value than tertiary amine. Further, the order of basic strength is as follows. Ammonia is a weak base than the primary amine. Primary amine is a weak base than a secondary amine, but secondary amine is a strong base than the tertiary amine. As per the observed pKb values of the aliphatic amines, secondary amines are the strongest bases. This is very clear from the pKb values which are less than the primary amines and less than the tertiary amines also. So they will be least and hence the basicity will be highest. The basic strength and corresponding pKb values depends on the position of equilibrium shown in the reaction below. That is amine reacting with water to form a conjugate acid and a hydroxide ion. If in this reaction the equilibrium shifts towards the conjugate acid, then the conjugate acid becoming stable by accepting a hydrogen ion makes the amine more and more basic. Now let us see the basic strength of aliphatic amines, how it is dependent on certain points. Greater the stabilization of the conjugate acid, the equilibrium will lie more on the RHS, and stronger will be the base with a smaller pKb value. Yes, we can utilize our brain power here to answer this question. Which compound from the following pairs is a stronger base? You can refer to the table 13.4 by going back in the video. So, amongst the first pair, methanamine and dimethylamine, you can observe that the second one is a secondary amine, so it has to be stronger than a primary amine. In case of second question, diethylamine is a secondary amine, whereas the second one is a triethylamine, which is a tertiary amine. So obviously again a secondary amine has to be stronger. In the last pair, we have to compare ammonia molecule with a primary amine, that is isopropylamine. So we have seen that aliphatic amines are stronger bases as compared to ammonia molecule. So in the third pair, the aliphatic amine isopropylamine will be a stronger base. So let us see the answers. Yes, so we can verify that in the first pair secondary amine, second pair also secondary amine, and in the third pair a primary amine are stronger bases. Now let us see the structural effects on basicity of amines. In that we will see the influence of plus I effect, that how a positive inductive effect makes a base more stronger. The influence of plus I effect on stabilization of conjugate acids of aliphatic amines and ammonia molecule is shown below. If you observe, the range is written from ammonium ion up to a tertiary amine converted into its conjugate acid. So ammonium ion has no positive inductive effect due to absence of any alkyl group. In primary amine, there is one positive inductive effect. In secondary amine, there are two positive inductive effects. In tertiary amine, there are three positive inductive effects. So keep this in mind and let us now verify what happens ahead with the basicity of these amines. The alkyl group exerts electron releasing inductive effect, which will stabilize the positive charge on atom bonded to it. So tertiary amine should have a strongest conjugate acid because its positive charge will be stabilized by electrons who are donated by three alkyl groups. This should result in increasing stabilization of conjugate acids, which thereby will increase the basic strength of compounds. So according to this statement, tertiary amines should be the most basic. Now let us see the influence of positive inductive effect and the order of stabilization. So this is the order of stabilization, that is ammonium ion is the least stable, whereas the conjugate acid of a tertiary amine is the most stable. Now expected order of basic strength will be that the tertiary amine should be the most basic amine, followed by secondary amine, followed by primary amine, followed by ammonia molecule. The expected order of basic strength on the basis of positive inductive effect differs from the observed order which is given below. So this was the order we have seen earlier, in which A secondary amine is stronger base than the tertiary amine. So if you compare the expected order of basic strength to the observed order of basic strength, the last two amines are showing a variation. The decreased basic strength of tertiary amines indicates that the conjugate acid of tertiary amine is less stable, even though positive inductive effect of 3 alkyl groups is expected to be large. So here is a glitch. This suggests the existence of another influencing factor in stabilization of conjugate acids of amines. So, along with the positive inductive effect, now we need to think about some another factor which is stabilizing these conjugate acids. So let us see the factor, and the factor is influence of solvation. Solvation of conjugate acids of aliphatic amines by water is represented as follows. So if you observe, the first molecule is ammonium ion solvated by 4 water molecules by hydrogen bonds of oxygen atom to the hydrogen of ammonium ion. The second structure is a primary amine having 3 water molecules solvating it. The third structure is a secondary amine having 2 water molecules solvating it. And last one is a tertiary amine where the hydrogen which has been accepted in the conjugate acid is forming a hydrogen bond with water molecule. So solvation is only by 1 water molecule. Now the solvent water stabilizes the conjugate acid by hydrogen bonding through the hydrogen bonded to the N+ ion. The number of hydrogen atoms bonded to N+ ion will decrease from 4 hydrogens in NH4+ ion to 1 hydrogen in the conjugate acid of a tertiary amine. As a result, NH4+ is best stabilized by solvation, while stabilization by solvation is very poor in tertiary amine, that is R3NH+. Now combined influence of positive inductive effect and solvation will give us the correct trend for basicity of these amines. The above two influencing factors operate in opposite directions. According to the positive inductive effect, the basicity increases from ammonium ion to the conjugate acid of tertiary amine, while solvation says that basicity increases towards the ammonium ion because ammonium ion is more solvated as compared to the other 3 aliphatic amines. Now the observed order of basicity is this, in which the strongest base is our secondary amine. Now conclusions from all this discussion are this, that basic strength increases from ammonia to R2NH, that is the secondary amine, due to better stabilization of corresponding conjugate acids. But tertiary amine is a weaker base than secondary amine, as stabilization of tertiary amine by solvation is a very poor solvation. Now let us consider the basicity of arylamines, which we saw in the table that the arylamines are least basic amongst all the amines. From pKb value, it is clear that arylamines are weaker bases than ammonia and aliphatic amines. The strength of arylamines is explained on the basis of Lowry-Bronsted theory. This is aniline, which is combining with water to form an anilium ion, that is a conjugate acid plus OH-. Both the species, base and the conjugate acid, are resonance stabilized differently. In case of base, electrons will be donated by the lone pair of electron on nitrogen atom to the ring, so ring will become electron rich, whereas in case of conjugate acid, the pi electrons which are present in the ring will come out of the ring to stabilize the N+ ion. The lone pair of electrons on nitrogen atom is conjugated to the aromatic ring and is less available for protonation. Aniline is resonance stabilized as follows. So you can see the 6 resonating structures of aniline where lone pair of electrons is donated in the ring, making the ortho, para and meta positions in second, third and fourth structure negative. So the ring is made active or electron rich by donation of electrons. Anilinium ion obtained by accepting a proton does not have lone pair of electrons on nitrogen. Hence it is stabilized by only 2 resonance structures. So when the aniline accepts a hydrogen atom from outside to become anilinium ion, it forms like this. You can observe the resonating structure that only the pi electrons will shift inside and you get the final answer. Thus, from both the resonating structures, that is from the resonating structure of aniline and resonating structure of anilinium ion, it is concluded that equilibrium in above reaction is shifted towards the left hand side, that is towards the base. This makes aniline weaker base than aliphatic amines and ammonia. So it is clear that due to the resonance structures which the aniline molecule is showing, it is becoming a weaker base than the aliphatic amines. I hope you have understood the basicity of amines in this video. Thank you for watching the video. Stay tuned for our next video on chemical properties of amines. Till then, bye.